Welcome to the Electrical and Electronic Engineering lecture series. Your anchor person is Professor Michael C. Ndinechi. Our topic today is Review of Electrostatics and Electromagnetism, Part 1. A body or an individual atom of that body is said to be or to have an electric charge when it acquires excess or is in deficient of electrons. When there are surplus electrons, the body is said to be negatively charged. On the other hand, if there is a deficiency, the body is positively charged because electrons carry negative charges. The starting point in the study of electrostatics is usually from the experimental investigations by Coulomb, who likened the electrostatic field associated with the charge on a body to the gravitational field associated with the mass of the body. Coulomb's law. Coulomb's law states that the force of attraction or repulsion between two charged bodies is proportional to the magnitude of their charges and inversely proportional to the square of the distance between them, as illustrated in Fig 1. In that Fig 1, the equation for the force will be given as K Q1 Q2 over R2 squared. Equation 1, where R is the distance between the two bodies, Q1 is the charge on the first body in coulombs, Q2 is the charge on the second body in coulombs, and K is a constant which is given as 1 over 4 pi epsilon equal to 10 raised to power minus 9 over 36 pi farads per meter for free space. Substituting the value of K in equation 1 gives F equals Q1 Q2 all over 4 pi R squared epsilon naught, where epsilon naught is the permittivity of the medium between the two bodies. This force acts in the direction of the line joining the two bodies. If Q2 is assumed to be the test charge, and if this charge is placed in an electric field where the field strength is E, then the mechanical force acting on the test charge is F equals QE, given in newtons per coulombs or volts per meter. So if we define the electric field strength as E as force per unit charge, then we have that E will be equal to F over Q. If we substitute the values, we have Q1 over 4 pi R squared epsilon naught. We call that equation 3. And in this equation 3, we take Q to be equal to Q2, since Q2 is taken to be the test charge. Now, electric flux density and electric flux. The electric flux density D, which was called displacement by Maxwell, is defined as the electric flux per unit normal area if the spherical surface of radius R, the total electric flux equals Q, and the area is 4 pi R squared. Then D is equal to the total flux over the area from definition, which we give Q over 4 pi R squared, which will be equal to epsilon naught E. Equation 4, where the surface is not everywhere normal to the electric displacement, then the total flux is given by phi equals integral over the surface of D ds, which is equal to Q. Thus, the integral of flux density over a closed equipotential surface must be equal to the enclosed charge. Gauss theorem. This states that the total electric flux passing through a closed surface is numerically equal to the electric charge enclosed by the surface. That is, phi is equal to integral of the phi over the surface S, which when expanded is equal to Q coulombs. Therefore, for a charged particle and a sphere of radius arrow meters, the flux density D will be given as Q over 4 pi r squared coulombs per meter squared. But dA is equal to Q, where A is equal to area of the sphere, which is 4 pi r squared. Then if we evaluate further, we have that E over D is equal to 1 over epsilon. Note, for free space, epsilon is equal to epsilon naught. Otherwise, epsilon is equal to epsilon naught, epsilon r, where epsilon is the permittivity, epsilon naught is the permittivity of the free space, while that of r is the material. Electric potential. This is defined as the work done by extraneous force against the forces of the electric field in moving a particle bearing a unit charge from one point to another. The difference in potential between x1 and x2 is given as dV equals minus E cos theta dx. If we differentiate with respect to x, we have it to be dV dx equals minus E cos theta. If the limit of the x tends to 0, it means that dV dx will be equal to minus E, because cos 0 is 1. Therefore, V is equal to minus integral of E dx, Ex dx, where V is the potential at point x2, or the work that must be carried out in bringing a unit charge from infinity at 0 potential to this point. The negative sign is an indication that the work is against the electric field. It is now possible to evaluate not only the electric field distribution of most conductors, but also the potential distribution and hence capacitance. Now, capacitance. If a body acquires or loses a charge, its potential changes by an amount which depends upon the charge gained or lost and the electrical capacitance of that body. When a voltage is applied between a neighboring pair of conductors, an electric field is set up between them, while an equal and opposite charges appear on their surfaces. If the conductors are in close proximity and of sizable area, the total charge on each may be considerable. The pair of conductors exhibit significant effects when placed in electric circuit if there is variation of voltage. In fact, an alternating current passes almost as if there is direct connection between the conductors. Such an arrangement constitutes a capacitor. Capacitance, therefore, is defined as the ratio of the charge on a conductor to the potential when all neighboring conductors are at 0 potential. We now say that capacitance C is equal to Q over V farads. Consequently, I is equal to C dV over dt. Parallel plate capacitors. Consider two parallel plates with area A separated by distance d and with the field normal to the parallel plate. If Q is the magnitude of the total charge on either plate, applying Gauss' law to the closed surface gives that D times A is equal to Q, but we already know that Q is equal to epsilon V. If E is clearly uniform and of magnitude V over D, with V being the voltage between the plates, then Q will be equal to epsilon VA over D. Therefore, C will be Q over V, which is epsilon A over D. Call that equation 9. For magnetic materials, C will be epsilon naught epsilon R A over D, where epsilon R is the permittivity of the material. We therefore say that the farad, that is the unit of capacitance, is the capacitance of a capacitor between the plates of which there appears a difference of potential of 1 volt when it is charged by 1 coulomb of electricity. The two plates separated by an insulator constitute a capacitor. To some people, it's called condenser. Such an arrangement has the capacity of storing electricity as an excess of electrons on one plate and deficiency on the other. Concentric cylinders. If we consider a hypothetical radius between A and B in Fig 3, we have, as before, V equals integral E dl. If we apply Gauss' law again over an equipotential surface, then A times D is equal to Q, which is equal to 2 pi RL times D. From whence, if we solve down, we get to equation 13. Further evaluation of equation 13 will give us equation 14. All these equations are very necessary when we consider transmission lines like coaxial cables and in finding the effect of passing current or voltage through them. Parallel cylinders. Consider two parallel cylinders of radius A and a voltage V applied between them as shown in Fig 4. Equal and opposite charges, that is plus or minus Q, appear on them separately in a length L. Consider the radius A to be small compared to the distance D between the conductors. Then the effect of one conductor on the charge distribution of the other is negligible. So electric field of 1 is given by E1 equals Q over 2 pi R LE. That of 2 is given as Q E over 2 pi LE into D minus R. The total electric field will now be E1 plus E2. So if we solve down, it gives us equation 16, which is C equals pi L epsilon over ln D over A, provided D is far greater than A. Thank you for listening. Like, share, and subscribe, and listen to part 2 of this topic, which is the concluding part.